Hello everyone and welcome to the sixth chapter of our Chemistry O-Level lesson series. This chapter is called Bonding and Structure. So without further ado, let's start. This chapter is called Bonding and Structure. Here we have the learning objectives of this chapter. The specific topics of the chapter are listed in the description below along with their timings, so you can watch them separately as well. Now, in this topic, you should be able to describe the formation of ions by electron loss or gain in order to obtain the electron configuration of an inert gas. You should be able to describe the formation of ionic bonds between metals and non-metals, for example, sodium chloride, calcium chloride, and potassium oxide. We're going to learn to state that ionic materials contain a giant lattice in which the ions are held together by electrostatic attraction. For example, sodium chloride lattice. We're going to learn to deduce the formula of an ionic binary compound from a diagram of its lattice structure. Describe the formation of covalent bonds by the sharing of a pair of electrons in order to gain the electron configuration of an inert gas. We're going to describe using dot and cross diagrams the formation of covalent bonds between non-metallic elements. Example, hydrogen, oxygen, water, methane, and carbon dioxide. We're going to compare the structure of molecular substances and macromolecule substances like diamond and graphite. Describe metals as lattice of positive ions in a sea of electrons. Relate the electrical conductivity of metals to the mobility of the electrons in the structure. Predict the physical properties of ionic compounds and relate these properties to their structure and bonding. And predict the physical properties of covalent compounds and relate these properties to their structure and bonding. So, these are the learning objectives of this chapter, Bonding and Structure. So, what are bonding and structure? Let's understand this first. Previously, we have learned how protons, neutrons, and electrons are arranged in atoms. So, it is the arrangement of these electrons, in particular the valence electrons, which is important in bonding. So, bonding is the way in which atoms join together and combine with one another. Okay? The arrangement of the resulting particles is called the structure. So when different atoms bond together, they make an arrangement. The particles make an arrangement, and that is called a structure. So remember, I even said in the previous chapter that valence electrons play a very important part in bonding. And we're going to see why and how valence electrons cause atoms to bond. But before that, it is very important with bonding to remember these points. Firstly, it is only the valence electrons in the outermost shells which become involved in bonding. The complete inner shells are not involved, only the valence electrons. The inner shells are not involved because they are complete. You know, I've said this in the previous chapter. Many atoms' outermost shells are not complete like their inner shells. Of course, their inner shells should be complete, only then there is another shell in which the electrons start moving. And I've told you that in the 8th group of our periodic table, we see inert gases. And we call them inert because they are not reactive. And that is because they are in the 8th group, which means that their valence electrons are 8, which means that their outermost shell is complete. And that is why they do not react. So it is this incomplete outermost shell which causes these atoms to bond. Because every single atom wants to have a complete outermost shell. Okay, so that's where we come to the second point, that it is the aim of every atom to achieve a noble gas structure. Because this gas structure, the noble gas structure, makes it very stable. So that is why every single atom is bonding with other atoms to complete their outermost shells. Number 3, the maximum number of electrons in the first shell is 2. We read this before as well. So the maximum number of the electrons in first shell is 2, and this is called a duplet. And the maximum number in the second shell is 8, and this shell is called an octet. So the maximum number in the third shell is 18, but in many elements, the electrons begin to fill the fourth shell when there are already 8 in the third shell. Because when the third shell has 8 electrons, it becomes more stable than if it had 18 electrons. So the third shell never gets up to 18, it always gets up to 8, and then the fourth shell begins to fill. And then when the fourth shell gets filled with 8, the fifth shell starts to get filled up, and that is how it goes. All the other shells, except for the first one, they all can take up to 8 electrons. So these are some of the points that you have to remember as we learn this chapter. That is, it is only the valence electrons in the outermost shell which become involved in bonding, and second, it is the aim of every atom to achieve a noble gas structure. That is why they bond. And 3, you have to remember all the different shells of an atom and how much each shell can hold up to. It's very simple. The first shell can hold up to 2 electrons, that is called a duplet, and any other shell after that shell can hold up to 8 electrons. Okay? Now we're going to look at ionic bonds. Ions and ionic bonds. So there are 2 different types of bonds, okay, first of all. One is the covalent bond and one is the ionic bond. So let's understand ions and ionic bonds first. So in this type of bonding, ionic bonding, atoms are joined together by electron transfer. Okay? This transfer involves the loss or gain of electrons, which results in the formation of ions. These are charged particles which are held together by electrostatic attraction. We've read about ions before. And ions are simply charged particles which are held together by electrostatic attraction, like positive ions and negative ions. Particles can be anything, molecules or atoms. Whenever we say particles, just think of molecules or atoms, okay? So these ions are basically these particles which are charged, either positively or negatively. And they are held together by electrostatic attraction. So if we bring a positively charged object to some negative ions, it would obviously attract it. They will get attracted because of the electrostatic attraction. So this is electrostatic attraction. These ions are charged particles which are held together by electrostatic attraction. And ionic bonding is basically when atoms get joined together by electron transfer, a loss or gain of electron, and the atoms get joined together. So to help explain this type of bonding, consider sodium chloride. This is a very common substance, better known as common salt, which is essential for life and completely harmless. But it is made up of 2 elements, sodium, which is explosive in air, and chlorine, which is extremely poisonous. So, how do 2 such dangerous elements, when combined, produce common salt, a harmless and very useful compound? The sodium atom is very reactive because of its electron arrangement of 281. It has only 1 valence electron in its third shell. So this valence electron is loosely held as it is furthest away from the attraction of the positively charged nucleus. So what sodium atom wants is to lose this 1 electron. When it will lose it, then it will have a stable configuration of 2 and 8. It achieves a stable full outermost shell or octet. And it also becomes a positively charged ion as it has lost a negatively charged electron. So remember, whenever an atom loses an electron, it will become positively charged. That means it will become an ion which is positively charged. Remember, why do we say this? It's because a negatively charged particle just leaves the atom. And so the atom would become positive, right? I mean, negative charge leaves the atom, then it will obviously remain positive. If it gains an electron, then it will become negatively charged. Because the proportion of negative and positive, the negative proportion becomes higher. So in this case of sodium, the sodium doesn't want another electron. You might be thinking, like, why do atoms gain electrons then? Well, they gain in some different cases. For example, if sodium had an arrangement of 287, that would not be sodium again. I'm just giving an example. If an atom had an arrangement of 287, then rather than losing an electron, it would need 1 more electron. And even if it had a 286 arrangement, it would need 2 more electrons because losing 4 electrons is not possible, it's not easy. So it would gain 2 electrons instead. But even if an atom had 282 electron arrangement, then they would prefer to lose the 2 electrons rather than gain 4 more electrons. Because it's much easier to lose 2 electrons rather than gain 6 electrons. it's almost impossible to gain 6 electrons. So that is why the sodium atom loses the 1 electron to another atom which needs 1 more electron, which in this case is chlorine. But before going over to chlorine, when the sodium atom loses this single electron, sodium achieves a stable, full outermost shell or octet. It also becomes a positively charged ion as it has lost a negatively charged electron. So here is how this is explained. Sodium with this electron configuration changes to this, plus 1 electron. So what happens is that the charge on the sodium ion is looked like here. The charge on 11 protons is equal to positive 11, and the charge on 10 electrons is equal to 10 minus 11, which when divided by positive 1, we get a charge of 1. What the hell, man? So sodium atom has 11 electrons, which means that it has 11 protons as well because they're equal. Okay, so the charge on 11 protons is plus 11, and when the sodium atom loses an electron, the charge on 10 electrons would be equal to minus 10. So basically what we're saying here is that first we have 11 protons and 11 electrons. So the negative and positive charge was equal, but the atom was not satisfied because it was not stable and the outermost shell was not complete. So it decided to lose an electron. When it lost an electron, the proportion of the negative charge of the atom became less than the positive charge in the atom. So now the protons are 11 and the electrons are 10, which means that the negative charge particles, electrons, are less than the positive charge particles, the protons. And that is a 1 charge difference. 1 electron represents 1 negative charge, and 1 proton represents 1 positive charge. And so the proton has 1 more positive charge than the electrons, and so that is why the total charge of the atom is plus 1, positive 1. If the sodium atom had given 2 electrons to some other atom, it would have a charge of plus 2, okay? And then in that case we would write plus 2 along with sodium's atom. Right now we do not write the 1 here, we just write a plus sign. But if it had lost 2 electrons, we would write 2 here. If it loses 3 electrons, we would write 3 here. So this is how the charge is. Now let's move over to the chlorine side. The sodium atom loses 1 electron to which atom? Obviously an atom which needs 1 electron, because both the atoms are taking something from each other. Both the atoms want their outermost shell to be complete, and so sodium bonds with chlorine because they are a perfect match for each other, as sodium has 1 extra electron and chlorine has 1 less electron. So sodium gives 1 electron to chlorine, both the atoms are now happy. Sodium loses 1 electron, it becomes stable, and chlorine gains an electron and becomes stable. So chlorine's electronic configuration is 287, which means that it is looking for an electron to complete its 3rd shell and thereby form a stable octet, because it's obviously very impossible for chlorine to lose 7 electrons to some atom and then become stable. Maybe it could have lost these 7 electrons to sodium, then both would have become stable, but atoms do not lose such big numbers of electrons. So the chlorine nucleus attracts an electron from the sodium atom and chlorine becomes a negatively charged chloride ion because it gained 1 electron, which means that the negative charge on the chlorine became more than the positive charge. So the charge on 17 protons was plus 17, the charge on 18 electrons is minus 18, which is more than the charge on 17 protons because the negative charge is 1 charge more than the positive charge. So the total charge is minus 1. In simple words, it gained an electron, it gained a negatively charged particle, which made it become negatively charged. If they lose a negatively charged particle, they would become a positively charged ion. Simple. So overall, we can represent this by using a dot and cross diagram to show the electrons in the different atoms. So here we have a sodium atom and a chlorine atom. One atom's electrons are shown by cross and the other atom's electrons are shown by dots. That is why it's called a dot and cross diagram, okay? So chlorine has 7 electrons, so they are highlighted like this. And sodium has 1 extra electron, that is why it is highlighted. So when they two add up together, this is what happens. The sodium loses this cross to the chlorine and the chlorine gets a full outermost shell. So sodium is left with a positive charge and the chlorine becomes negatively charged, like this, okay? So in ionic bonding, there is a transfer of electrons rather than a sharing of electrons. So there are two different types of bonding, as I said in the beginning, that one is ionic bonding and the other is covalent bonding. And in ionic bonding, the electrons are transferred. But in covalent bonding, the electrons are shared. And so that is why their dot and cross diagram would be different from the ionic bonds dot and cross diagram. So if you have ever seen a dot and cross diagram like this, something like this, don't confuse it with this type of diagram I'm showing here. They're two separate things, different from each other. This kind of diagram represents ionic bonding because the sodium transfers one electron to chlorine and it is left with no electrons and the chlorine gets one electron. So this is how dot and cross diagram represents ionic bonding. But the dot and cross represents covalent bonding as well, but in a different way. That is something like this, because in covalent bonding, the electrons are shared. We're going to see that later in just a moment after I show you some more examples of the dot and cross diagrams. Some other ions: potassium fluoride, magnesium oxide, calcium chloride, potassium oxide. So in potassium fluoride, potassium has one extra electron in its outermost shell. Remember, the electron shells can hold up to only 8 electrons. So whenever we're saying that an atom has one extra electron, we don't think that the outermost shell is filled with 9 electrons, okay? That's not right. What we think is that the outermost shell is filled with only 1 electron. Do not think of this extra electron in a shell which already contains more electrons, because that is not possible. Every single shell, except for a duplet, can hold up to only 8 electrons. So this single extra electron can only be alone in one shell, and extra 2 electrons as well, or even 3. I hope you're not confusing this. I don't know why I'm telling you this, but I just thought of it, that you might be thinking maybe there are 9 electrons in the outermost shell of potassium. But that's not correct, because all the other shells except for a duplet can hold up to only 8 electrons, not 9. So that is why this extra electron is always in a shell which is completely empty and only with this 1 electron or these 2 electrons. Okay, let's move ahead from this. Potassium has 1 extra electron and fluorine has 1 less electron. It has 7 electrons in its outermost shell. It needs 1 more to fill it, and so they bond together. They become potassium fluoride. But over here it's a kind of different. We have magnesium, which contains 2 extra electrons, and it finds a perfect match for it to become stable: oxygen, which has 6 electrons in its outermost shell. You know, oxygen is in the 6th group of the periodic table. Why? Because it contains 6 valence electrons. We read this, that the group number indicates the number of valence electrons in an atom. So they both bond together. Magnesium loses 2 electrons to oxygen. Oxygen gains 2 electrons, and both atoms are happy. They form magnesium oxide. Then we have calcium chloride, and this is a very different bonding as well here. Ionic bonding, obviously. Calcium here has 2 extra electrons. Now, calcium can also find an atom like oxygen. It can also make calcium oxide, but instead of doing that, it bonds with 2 chlorine atoms. Yes, an atom can bond with 2 atoms at the same time if it has 2 electrons. So calcium has 2 electrons and chlorine atoms have 7 electrons in their outermost shell, like we read before. 1 chlorine atom needs 1 more electron in its outermost shell. So 2 chlorine atoms would need in total 2 electrons. So when these 2 atoms bond with 1 calcium atom, they form calcium chloride. And so that is why their chemical formula is CaCl2, calcium chloride 2, because there are 2 atoms of calcium here. Now we can just reverse this entire thing and make it potassium oxide, which is K2O. In here we have 2 atoms which have extra electrons, each of them has 1 extra electron. Potassium has 1 extra electron, like we saw here, and oxygen needs 2 electrons. So 2 potassium atoms join with oxygen. Each of them gives their single electrons to oxygen, which gains the 2 electrons, and they bond together to form potassium oxide. So when potassium gives electrons to oxygen, it gains a positive charge because negative particles are leaving the atom, whereas oxygen becomes negatively charged because negative particles are entering the atom. And because 2 electrons are entering oxygen, it would have a charge of -2. It was not written here actually, that's why I just wrote it here. So when calcium loses 2 electrons, it would have a charge of +2. We don't write it +2, we write it 2 plus, even though we pronounce it like that, and we write it 2 minus or only minus. Whenever we write only one sign, like 1 plus sign, one addition sign, that means that it is a charge of 1 positive charge. If it is just a minus sign, it is 1 negative charge. So we do not write 1, we just write these signs to indicate 1 charge. But when the charge goes more than 1, like 2, we would write it down like this before the symbol, 2 plus, 2 minus. That is how it's done. So remember, an atom loses electrons, it becomes positively charged because negative particles just left the electron, the positive particles are now increased in proportions to the negative particles, and so on. They become positively charged. And if an atom gains the electrons, it becomes negatively charged because negatively charged particles have just entered the atom. So the proportion of the negative charge increases than the positive charge, causing it to become negatively charged. Okay? I hope all of this is clear now. So this is how bonds are formed. One atom can bond with 2 different atoms. 2 atoms can bond with 1 atom. Oh, it's actually the same thing. What I'm trying to say is that a single atom can transfer 2 of its extra electrons to 2 different atoms, each of which need 1 extra electron. Or 2 atoms which both have 1 extra electron, they both can give their single electrons to an atom which needs 2 electrons, like oxygen, and can bond like this as well. CaCl2, K2O. Or just keep it simple, 1 electron from one atom to an atom which needs 1 electron. Then we don't have to write any digits here. It just remains potassium fluoride, Kf, magnesium oxide, MgO. Because magnesium has 2 extra electrons and oxygen has 2 less electrons, they just transfer them. You don't have multiple atoms here. But in this case, like calcium chloride, we have 2 atoms which are receiving the electrons and only 1 atom which is giving the electrons. So we write it as CaCl2 because there are 2 chlorine atoms. And in potassium oxide, we have 2 atoms which need to give their electrons and 1 atom which needs these 2 electrons, and they form potassium oxide, K2O, because there are 2 potassium atoms and only 1 oxygen atom. Now that we've understood ionic bonding, as you can see, it's very simple. All they do is that transfer their electrons and gain charges. They become ions. So both the atoms get opposite charges, as you can see. These 2 potassium atoms gain a positive charge and this oxygen atom gains a negative charge, which cancel each other out basically, because -2 is oxygen's charge and +2 is potassium charge. As you can see, the 2 atoms have 1 charge and together they make 2 positive charges, and so they, in simple words, they just get cancelled out by each other because they're equal to each other, and so they form a compound which is neutral. So remember, they do not form ions. Ionic bonding doesn't form ions, they form compound, okay? So these are different ions. Of course, potassium atom is an ion because ionic bonding causes the atoms to become ionized because they gain electrons and they lose electrons, but when they bond together, they become stable. They gain different charges, but in the end, they all just get cancelled out, and the end product which is formed is neutral. It's stable, okay? Simply, it's stable. 2 or 3 unstable atoms join to form a stable compound, okay? So, ionic bonding is important between metals in groups 1 and 2 of the periodic table, and non-metals in groups 6 and 7. So the groups in the middle of the periodic table contain too many electrons in their outermost shells to form ions, as it would involve too much energy to lose or gain 3 or 4 electrons. But the aluminium ion is an exception. So usually, atoms only lose 1 or 2 electrons. Losing or gaining 3 or 4 electrons would involve too much energy. So that is why the groups in the middle of the periodic table do not form ions, because they have too many electrons in their outermost shell. So this is what ionic bonding is. Now we're going to move ahead on to looking at the covalent bonding. So this type of bonding is an alternative to ionic bonding, favored by non-metallic elements and their compounds in groups 3, 4 and 5. Because ionic bonding does not occur in groups 3, 4 and 5, because the elements in these groups contain too many electrons in their outermost shell, and ionic bonding involves the transfer of electrons. So to lose or gain 3 or 4 electrons would involve too much energy. So that is why ionic bonding does not happen in groups 3, 4 and 5. So in these groups we have covalent bonding which occurs. So that is why we're saying that covalent bonding is an alternative to ionic bonding and is favored by non-metallic elements in groups 3, 4 and 5. So how is it an alternative to ionic bonding? In ionic bonding we are transferring electrons, which causes too much energy. But in covalent bonding, we share electrons. So this type of bonding involves electron sharing with no transfer. Accordingly, no charged particles are formed, only groups of atoms called molecules. Now remember, only covalent bonds form molecules, okay? Ionic bonding does not form molecules. Ionic bonds form ionic compounds. So all of these like potassium fluoride, magnesium oxide, these are not molecules because there is a transfer of electrons, and doing that they do not form molecules, they form ionic compounds. Because ionic bond is known as the strong electrostatic attraction between adjacent cations and anions, positive and negative ions basically. So the ionic bond is basically this strong electrostatic attraction. When these form, both the atoms, the one which is gaining electrons becomes negatively charged, and those which are losing electrons become positively charged. So when they do this, they form unlike charges, which makes them attracted to each other. So it is this electrostatic attraction between them which keeps them together and makes them these compounds, but not molecules. Ionic bonding does not form molecules, it only forms ionic compounds, okay? Because they're not actually joining with each other. This is just the electrostatic force which keeps them stick together. But they are not actually joined with each other. They just transfer the electrons and their work is done. This atom transfers its electrons to this one, and that's it. I mean, they can also go to their separate ways, but they don't do it because the electrostatic forces keep them together. And that is how an ionic compound is formed, not a molecule. Okay? Ionic bonding does not form molecules, but covalent bonding does. Because covalent bonding involves electron sharing with no transfer. And so, because of this, no charged particles are formed, no ions are formed. So no electrostatic forces come in between, and only groups of atoms are formed which are called molecules. So to explain this type of bonding, let us consider a simple molecule. For example, chlorine. So each atom of chlorine has 7 electrons in its outermost shell. Its electronic configuration is 287, which means it is 1 electron short of the stable octet in the third shell. And it achieves stability by sharing 1 electron with another chlorine atom, which in turn shares one of its electrons. This shared pair of electrons form a single covalent bond. Okay, so what just happened? A chlorine molecule needs an electron to complete its outermost shell. Now we put another chlorine molecule which also needs another electron to complete its outermost shell. And another chlorine atom, obviously it is similar, it is the same chlorine atom, just make a duplicate out of it. It also needs 1 more electron to make a stable octet. So as you can see here, electrons are in pairs. We have 6 electrons and 1 electron which is alone here. So does this atom of chlorine also. So what happens is that the chlorine atom shares this electron with the other chlorine atom. This chlorine atom shares its extra electron with the other chlorine atom. So in simple words, they both share one of their electrons to each other and form a stable octet. Okay, so they share one electron, something like this, as you can see. Now both the chlorine atoms have 2 electrons. Because in this we are not transferring, do not confuse it with it. You might say, why, how can they get so stable? I mean, the electrons in both the atoms are still 7, even if they start sharing one of the electrons, but no. When this electron of this chlorine atom goes into this chlorine atom has 8 electrons. And if one electron this chlorine atom goes into this chlorine atom, this also has a stable atom 288. Because they are sharing their electrons. Okay, so we have 6 electrons over here in this atom and 6 electrons over here in this atom and 2 in the middle. So 6 plus 2 is 8. And for this atom it is also the same. So for both the chlorine atoms it is the same. For this chlorine atom we have 8 electrons. 6 plus these 2. Yes, we're counting this chlorine atom's electron as well. It becomes 8. And so is the same for this chlorine atom. The electrons become 8. Because they're sharing these electrons, their atomose shells become complete. So this is covalent bonding. We either show it like this, or when we're writing it down, we write it like this: Cl dash Cl. So this is basically a molecule, chlorine molecule. Ionic bonding doesn't form molecules, covalent bonding forms molecule. And in covalent bonding, we are sharing electrons. But in ionic bonding, we are transferring electrons. And transferring electrons involves energy. And it involves charges. And it involves the electrostatic attraction and repulsion kind of thing, which causes them to stick together. Whereas in covalent bonding, all we have is just sharing. They share together their electrons, they stick together. Obviously, when they're sharing, they would have to be together. And so they form molecules. In ionic bonding, they do not form molecules because the atoms are not actually combining together. They're not combining together. They just transfer their electrons. And they can actually go off their separate ways, but they can't because of the electrostatic forces between them. Positive and negative charges attract, and so they just get attracted together. But in covalent bonding, they are sharing electrons, so they are actually joining with each other. They are basically combining with each other. So this is how chlorine molecules form. We read in the previous chapter about diatomic molecules, and in those we saw molecules of the same element. Like chlorine is an element. We have a chlorine atom, but we also have chlorine molecules. That happens when 2 chlorine atoms join together, they form a chlorine molecule. And so this basically is the chlorine molecule. Even though chlorine itself is an element, usually the molecules which are formed are not the elements, but yes, chlorine itself is an element as well as a molecule. But remember, there's a difference between both of them. The element is simply written as Cl, but in a chlorine molecule, we write it as Cl2 because there are 2 atoms of chlorine. So we write it as Cl2. Now consider oxygen gas. Each atom of oxygen has 6 electrons. Look at the outermost shell, not this shell. Okay, this one is the duplet. That is filled in both the oxygen. But both the oxygen atoms have 6 outermost shell. 1, 2, 3, 4, 5, 6. Counting the green ones, and when you count the yellow ones, we also get 6. So its electronic configuration is 286, which means it is 2 electrons short for the stable octet. So it achieves stability by sharing 2 electrons of another oxygen atom, which in turn shares 2 of its electrons. So as a total of 4 electrons are shared by the 2 oxygen atoms, they form a double covalent bond. So this one in the chlorine one is a single covalent bond because 1 pair of electrons are being shared. But over here 2 pairs of electrons are being shared because oxygen is 2 electrons short for a stable octet. That is why we have a double covalent bond. The other one is a single one because we have only 1 pair. And we write the double covalent bond something like this with 2 dashes in the middle. A single covalent bond has only 1 dash in the middle. But in double covalent bond, it's like an equal sign. 2 dashes, which represent 2 electrons basically, double covalent bond. So, I hope you've understood covalent bonding. It's pretty simple. Atoms just share their electrons. This oxygen atom shares 2 of its electrons and this oxygen atom shares 2 of its electrons, and the electrons that they're sharing are theirs as well. So we count those in the atom. 1, 2, 3, 4, 5, 6. And then we count the other atom's electrons as well. 7, 8. complete octet. In the same way, this oxygen atom has 6 electrons, counting those which it is sharing as well. And then we count those of the other oxygen atom which it is sharing, and we get 8 electrons, a stable octet. Just sharing 4 electrons together, both the oxygen atoms are stable now. They form a double covalent bond. So this is what covalent bonding is. Here we have some other common examples of covalent molecules. First we have hydrogen. In this, there is only a single covalent bond, as you can see, because both the hydrogen atoms share only one of their electrons, and so they're sharing only one pair of electrons. So that is why it's a single covalent bond. Methane has 4 hydrogen atoms bonding with 1 carbon atom. Water has 2 hydrogen atoms bonding with 1 oxygen atom, and these two all have single covalent bonds here. So does ammonia. 3 hydrogen atoms bonding with nitrogen, all having single covalent bonds. But over here in carbon dioxide, we have 2 oxygen atoms bonding with 1 carbon atom, and both of them are having double covalent bonds. So they're sharing 2 electrons of their atom with the carbon atom. So the carbon atom in total is sharing 4 electrons with both the oxygen atoms, 2 to each atom. So this is what dot and cross diagram is made for covalent bonding. As you can see, it's very clear that the electrons are being shared. But in the ionic bonding, the electrons are not being shared, they're only being transferred. So that is why they're shown something like this. So the thing to remember about here is that in covalent bonding, electrons are being shared, and in ionic bonding, electrons are being transferred. So when electrons are being shared, both the atoms are together because they're sharing electrons. They move together and they make molecules because they are combining together, as you can see. They go into each other, they share the electrons, so they are basically combining together and they form molecules like this. But in ionic bonding, electrons only get transferred. So one atom has 1 extra electron and the other atom needs it, so it just transfers this 1 electron to that atom, and they can also go their separate ways after this, but they don't, because the charges on them causes them to have an attraction. The one which gains the electron becomes negatively charged, and the one that gives the electron becomes positively charged. And so this electrostatic charge causes both the atoms to get attracted to each other and they join together basically. But they don't form any molecule because they're not combining together, they're just joining together from the outside. It's just the attraction, the electrostatic charges that cause them to join together to form these ionic compounds. So they don't form molecules, they form ionic compounds like these. And of course these ionic compounds they don't have any charge because all the charge gets cancelled. If both the atoms, when one atom gives an electron to the other one, both have equal charges. The fluorine atom in this case has 1 negative charge and the potassium atom has 1 positive charge, and they're equal in proportion as well, 1 charges, and they're opposite to each other. That is why they cancel each other out. 1 negative charge, 1 positive charge, they cancel each other out, and then the entire compound is neutral. Even when an atom is giving 2 electrons, then the atom which is receiving it is also receiving 2 electrons. And in simple words, they both have equal charges. So the end product always has no charge. It's always neutral. And in covalent bonding, there is no thing as charging or electrostatic attraction or repulsion because the electrons are being shared. They're not being transferred, and so no charged particles are formed. Charged particles are only formed when ionic compounds are formed. And these charged particles are atoms basically, are only formed when electron transfer occurs. But in the end product that the 2 charged particles form is always neutral because the charges get cancelled out by each other. Okay, so I hope you've understood all of this. You've understood the dot and cross diagrams of both the covalent bonding and the ionic bonding as well. So now we're going to move ahead onto crystal lattices. The ions that are formed by electron loss or gain are regularly arranged in the form of a giant crystal lattice. For example, salt. Salt is also in the form of tiny crystals, something like this. if you see normal salt, they make it even more fine by crushing it, but salt is also in the form of crystal lattices because salt is also an ionic compound. So the ionic compounds formed by electron loss or gain are regularly arranged, and the end product of this arrangement is a crystal lattice. So this is the salt crystal lattice, the sodium chloride crystal lattice, and this is the regular tube shape of the sodium chloride crystal. So these lattices are very stable due to the strong electrostatic forces between the ions. And so accordingly, most ionic compounds are solids with high melting and boiling points. Some of these compounds like magnesia and alumina are so stable that they are used as refractory material, which is used to line the inside of furnaces. And inside furnaces there is very high temperature. So these substances must be stable up to at least 1500 degrees centigrade. So what I'm trying to say is that crystal lattices, because they're made up of these electrostatic forces between ions, that's the reason why they are so stable. And it is really difficult to break them apart, break these electrostatic forces. Even heat cannot do it. And another property of crystal lattices is that they are non-conductors of electricity. They do not conduct electricity. This is because the ions are in fixed positions and are unable to move. So the positive and negative charges cannot flow anywhere. They are fixed in positions. That is why they are non-conductors of electricity. So these are the crystal lattices. I hope you've understood. Basically, the ions formed by electron loss or gain are regularly arranged in the form of a giant crystal lattice. That is how crystal lattices are formed, and these are very stable because of the electrostatic forces between the ions, and they are non-conductors of electricity. Now, let's look at the structure of covalent compounds. So, covalent compounds can be divided into those which form small, simple, independent molecules and those which form giant molecular lattices. Okay, first we're going to see the covalent compounds which form small, simple, independent molecules. These are molecular compounds. These molecular compounds are made up of independent molecular units. And as there are no ions formed, the attractive forces between molecules in solid covalent compounds like iodine and sulfur are much weaker. And these are called van der Waals forces. These produce a weak molecular lattice with low melting points. So, this covalent bonding makes covalent compounds, and these covalent compounds are divided into those which form small, simple, independent molecules and those which form giant molecular lattices. The small, simple molecules are the molecular compounds. They are made up of independent molecular units. They are very simple, and they're simple because there are no ions formed. And the attractive forces between molecules in solid covalent compounds like iodine and sulfur are much weaker. And these weak attractive forces between these molecules are called van der Waals forces. So here we have strong covalent bonds between the atoms, and then we have this entire lattice. It's a molecular lattice, but unlike the ionic lattices, these have much weaker attractive forces between these molecules. So weak intermolecular forces between molecules, and these are called van der Waals forces. In covalent liquids like water, the molecules are even further apart, so the van der Waals forces are weaker still. And in covalent gases like ammonia and methane, these forces are almost non-existent. However, in water, there are other attractive forces between molecules, and these forces are called hydrogen bonds. And they gave water much higher melting and boiling points than expected with such weak van der Waals forces. So, van der Waals forces are weak, attractive forces between molecules in solid covalent compounds, okay? In covalent liquids like water, the molecules are even further apart, so the van der Waals forces are weaker still. But there are other attractive forces between molecules of water, and these forces give water a much higher melting and boiling point than expected with such weak van der Waals forces. But it's only water, okay? The other liquids, the other covalent liquids, they all have weak van der Waals forces. They are weaker. And in covalent gases, these van der Waals forces are non-existent. But in water, there are some things called hydrogen bonds, which we will look at afterwards in some other chapter. These hydrogen bonds make water a much more stable compound. Okay? So, this is the first group of covalent compounds we've seen, okay? These are the compounds formed from small independent molecules. These are the molecular compounds, and now we're going to look at those covalent compounds which form giant molecular lattices. And these are called macromolecular compounds. Now, these have giant covalent molecules with extremely large molecular lattices. And unlike the other covalent compounds, the molecular compounds, these lattices are very stable, as all the atoms are joined together by strong covalent bonds to give a giant three-dimensional lattice. Often, the lattice is tetrahedral in shape, as every atom is covalently linked to 4 others. Here you can see the shape of these lattices. So, the macromolecular compounds have giant covalent molecules with extremely large molecular lattices, and they are very stable because all of their atoms are joined together by strong covalent bonds to give a giant three-dimensional lattice. And this lattice is often tetrahedral in shape because every atom is covalently linked to 4 other atoms. As you can see, this blue atom is linked to 4 other atoms. So in this lattice, this is a sand lattice, silicon dioxide. It is made up of 2 atoms, silicon and oxygen atoms, okay? And this is a 3-dimensional lattice, and this a tetrahedral lattice in shape, because each silicon atom in this lattice is surrounded by 4 oxygen atoms. It is called tetrahedrally arranged because every atom is covalently linked to 4 other atoms. Examples of such macromolecules are diamond, this is sand, and a diamond crystal or grain of sand is just one giant molecule. Such molecules, because they are so rigid and strong, have very high melting points. So, it's really difficult to melt sand, isn't it? Because it is a macromolecule, like a macromolecular compound. And in these compounds, every atom is linked with 4 other atoms. So this is what macromolecular compounds are and molecular compounds are. These are the 2 different structures of covalent compounds. I hope you've understood it, understood the van der Waals forces, and you've also understood the crystal lattices the ions form. These are crystal lattices, and they are formed by ions. Then the molecular compounds, the macromolecular compounds, are formed by covalent compounds. And you've understood this tetrahedral shape of these lattices. So now we're going to move ahead onto understanding metallic bonding. So, metals are electropositive in nature. That is, they have a tendency to lose their valence electrons to form positive ions. Basically, usually metals do not gain electrons, they lose their valence electrons. And when they lose their valence electrons, they form positive ions. So, that's what we're saying, that metals are electropositive. They have a tendency to lose their valence electrons rather than gain valence electrons. And that is because of the number of valence electrons they have in their outermost shell. They're probably less than 4. So when we have less valence electrons, usually they're going to lose these valence electrons, because gaining a large amount of valence electrons is not possible in ions, as it requires too much energy. So here in metals, as the atoms are packed so closely together, the outermost valence electrons become delocalized. And this results in a closely packed, regular arrangement of positive metal ions surrounded by a sea of mobile valence electrons that bind the ions together. So, this is what we are saying, that these atoms of the metals are so closely packed together that their valence electrons become delocalized. So they can go anywhere. They can go in another atom's electron shell as well. It's like the entire path is joining, all their paths are joining with other atoms, and they become delocalized. So the result is a regular arrangement of positive metal ions surrounded by a sea of mobile valence electrons that bind the ions together. Yes, these valence electrons bind the ions together. And so when a metal is connected in a circuit, these freely moving valence electrons move to the positive terminal. And to replace them, more electrons are fed into the metal from the negative terminal. And so that's how this entire chain keeps on going. So metals are therefore good conductors of electricity. Now this three-dimensional close packing of metallic ions also gives metals their other characteristic properties. So free valence electrons make metals good for the conduction of heat as well. The heat energy can be transferred from one ion to the next by vibration because they're so close together that one atom starts moving. Because of that kinetic energy, it starts moving. It moves all the other atoms around it as well. Because like this atom starts moving, these two atoms would start moving too because of this, and then these would cause these four atoms to start moving, these four would cause all of the other atoms, and so on. That is how the metals are good conductors of heat as well, because their atoms are so closely packed together. And this three-dimensional close packing of metallic ions also makes metals strong with high densities and high melting points. Density is basically the mass per unit volume. And the more atoms there are in a particular volume, the higher the density will be. So the more the mass, the higher the density. And the less the volume, the higher the density. So, like if we keep the mass at its fixed position and the volume decreases, then the density would become higher. And if the volume is kept static and the mass is increased, then the density would also increase. And so because their atoms are so closely packed together, metals are strong with high densities and high melting points. Because of their attraction, it's a little difficult for the heat to actually affect these atoms to melt down easily. So that is why they have high melting points. They have good electrostatic attraction. So they are stable basically. Metals are very stable. Now, you might be thinking that they're strong, they are dense, they have high melting points, they're good conductors of heat, and so metal itself are like very hard solids. Even though all these structures are strong, they are not rigid in any way. They're not rigid, like they are not difficult to shape. It's not difficult to shape these. So this structure, even though it's strong and everything, it would allow an external force to cause the layers of its particles to slide over one another. And this gives metals their malleable and ductile properties. So when we heat a metal, we can shape it. Like you can slide it, you can twist it, you can elongate it, you can compress it. So basically, the metal is malleable and ductile. It can be formed, it can be changed, its shape can be altered. So that is why the metal is strong and everything, but it's not rigid. Okay? By malleable, we mean that they can be hammered into different shapes, and by ductile, we mean that they can be pulled out into wires as well. Ductile means that we can like stretch them into very thin things as well, something like that. Anyways, we are able to change them into any shape we want. That's what malleable and ductile means. So this was metallic bonding. I hope you've understood it and what the structure of metals are, which makes them good conductors of electricity, heat, and makes them very strong with high densities, but it doesn't make them rigid. They are also malleable because the external force causes the layers of particles to slide over one another. And so that is why they're malleable. And they're electropositive. So now we're going to look at the comparison between ionic and covalent substances and some of their properties. So, comparison between ionic and covalent substances, starting first with volatility. So volatility is basically the melting and boiling points and stuff like that. So ionic substances are usually solids with high melting and boiling points. This is because there are strong forces of electrostatic attraction between oppositely charged ions, and so this results in stable structures called crystal lattices, which are difficult to melt. We've read this before previously about in ions that they are solids. Ionic substances are solids usually with high melting and boiling points. Why are they difficult to melt and difficult to boil? Because their atoms have very strong forces of electrostatic attraction, because they're oppositely charged. After transferring their electrons, both different atoms gain different charges which are opposite to each other, and this electrostatic attraction makes them very strong, makes their bond very strong, and this results very stable structures called crystal lattices. Inside these lattices, the ions are always packed in a regular fashion to give an overall shape to the crystal. So with a sodium chloride lattice, the ions are packed into cubes, so the overall shape of its crystal is cubic. Covalent compounds are normally gases. Unlike ionic substances which are usually solids, covalent compounds are normally gases, volatile liquids, or solids with low melting and boiling points. So, this means they can evaporate easily and give off a smell. Such covalent compounds can therefore be used as flavorings or perfumes. So covalent compounds are quite the opposite from ionic substances in volatility. Covalent compounds are normally gases, volatile liquids, or solids, and they have low melting and boiling points because we read before they don't have strong electrostatic attraction between their molecules, and they have some weak forces between their molecules which are called van der Waals forces, and that is why they have low melting and boiling points, so they can evaporate easily and give off a smell. And that is why we use such covalent compounds as flavorings or perfume, because they give off a smell, they evaporate easily, like perfumes evaporate easily and give off a smell. Fuels like petrol and natural gas are also covalent molecules, as are the substances inside fire extinguishers and aerosols. So both covalent compounds and ionic substances are used in different places. So we don't compare with them in such manner that which one is better than the other. We're basically comparing between ionic and covalent substances, that what are the properties of both the different substances and what can they do, how are they different from each other, not comparing them which one is better than the other. Both are different. Ionic and covalent substances are both different and have their own different uses depending on their properties. Next, we have solubility. So most ionic substances dissolve in water because water, although covalent, has a separation of charge. So this separation of charge is called polarization, and it causes water molecules to arrange themselves around the ions. The positive ions attract the negative side of the water molecule, which is the oxygen end, and the negative ions attract the positive side of the water molecules, which is the hydrogen side. So this is what polarization is. So even though water is a covalent compound, it's a molecule, it does have a separation of charge. And that is how these water molecules arrange themselves around the ions because of these charges. And this is called polarization. So the ionic substances dissolve in water, but they also charge the water up a little. That's what we're saying, that's what polarization is. But most covalent compounds do not dissolve in water. They are insoluble. However, they will dissolve in solvents which have no polarization, such as alcohol, tetrachloromethane, or petrol. These are called organic solvents. So the solvents which don't get charged up when ionic substances dissolve in them, and they don't arrange themselves around the ions like water does, because it does have some sort of charge. It has a separation of charge. Covalent compounds do not dissolve in water. They will dissolve in solvents which have no polarization, such as alcohol, tetrachloromethane, and petrol. And such substances, such solvents, are called organic solvents. Then we have electrical conductivity. Ionic compounds, when they are solid, do not conduct electricity. However, when molten or dissolved in water, they do conduct electricity. This is because the ionic crystal lattice is broken down so the ions can move, and these moving ions carry the electric current. So ionic compounds in solid form do not conduct electricity, but in liquid form, whether they are molten or dissolved in water, they conduct electricity. Because when they are solid, their ions are closely packed together with their attractions very tightly held together, all the atoms, and the ions cannot move. But when the ionic crystal lattice is broken down so the ions can move, these moving ions carry the electric current. They can carry the electric current because then they are moving, okay? Covalent compounds, however, are poor conductors of electricity, even when molten. And this is because they do not contain ions but are made up of molecules which cannot carry the electric current. So, covalent compounds are quite the opposite of ionic compounds. They are poor conductors of electricity whether they are molten or not. And this is because they do not contain ions. If there are no charges in a molecule, like a positive or negative charge, how would it be able to conduct any electricity? So, covalent compounds are made up of molecules which cannot carry the electric current. Now, you might be thinking ionic compounds are like the best compounds. They can do anything. They can conduct electricity. They are soluble in water, and they also do some sort of polarization thing with water. And they are solids with high melting and boiling points. They are like strong. In terms of electrical conductivity, ionic compounds are better than covalent compounds. But this is not how we compare in chemistry. We don't say that something is better than the other thing. Whether it's in the case of electrical conductivity, solubility, that covalent compounds are better than ionic because they dissolve in water, or in volatility, that covalent compounds are more volatile than ionic substances. That's not how we compare these. Using the words poor and good may sound like we are comparing and we're saying that the covalent compounds are poor, they're not as good. But basically what we're saying is that they're not as good in conducting something, which is not a bad thing. That's what they are. Covalent compounds, they are poor conductors of electricity, and ionic compounds are good conductors. That doesn't make ionic compounds better than covalent compounds. It doesn't make sense that ionic compounds are far better than covalent compounds. But covalent compounds, because of these characteristics, are used at different places. They are also made use of. They help in different circumstances, and ionic compounds help in different circumstances because of their characteristics. Ionic compounds dissolve in water, and most covalent compounds do not dissolve in water, which makes covalent compounds different from ionic compounds, and we can use them at places where we can't use ionic substances. And we will use ionic substances at places where we can't use covalent substances. So, all these characteristics are what makes covalent and ionic substances different from each other. So, this was all the comparison between ionic and covalent substances, the volatility, the solubility, and the electrical conductivity. Now, we're going to see the properties of ionic and covalent substances. Here we have this table of properties of all these substances. Ionic and covalent, here we have the substances with their melting and boiling points and their solubility in water and their electrical conductivity when molten. Okay, so let's start with the ionic substances first. We have sodium chloride. So the ionic substances is not a molecule. Its melting point is 801 degrees centigrade and boiling point is 1413 degrees centigrade. And sodium chloride is soluble in water and is a good electrical conductor. Copper 2 chloride actually has a melting point of 320 degrees centigrade and a boiling point of 990 degrees centigrade and is soluble in water and a good conductor. Potassium bromide has a melting point of 728 degrees centigrade, a boiling point of 1376 degrees centigrade and is soluble in water and is a good conductor of electricity. Calcium chloride also has very high melting and boiling points like 778 degrees centigrade melting point and 1600 degrees centigrade boiling point and is also soluble in water and a good electrical conductor. So ionic substances, as you can see, have very high melting and boiling points. They all are soluble, at least the ones that are given here, and they are all good conductors of electricity. Now we get to covalent substances like methane. Methane has a melting point of minus 182 degrees centigrade and a boiling point of minus 161 degrees centigrade. It is insoluble in water, like it's completely insoluble in water, and is a poor electrical conductor. Carbon dioxide has a melting point of minus 78 and a boiling point of minus 78 degrees centigrade. I have told you why the melting and boiling point is equal in carbon dioxide. We read about this in the second chapter of this chemistry O-level series, and particles of matter. And carbon dioxide is slightly soluble in water and is a poor conductor of electricity. Water has a melting point of 0 degrees centigrade and a boiling point of 100 degrees centigrade and water is water, so there's no solubility of water. But water is a poor electrical conductor. But still, don't think that knowing this would not get you electrocuted when you put wet hands in an electric switch. That is still hazardous. Never put water in electric switches or in any electric device. At least don't touch it when your hands are wet, okay? Even though water is a poor conductor. Then we have iodine, which has a melting point of 114 and a boiling point of 184. And it is slightly soluble in water, and it is a poor electrical conductor. And lastly, we have sulfur, which has a melting point of 114, just like iodine, and a boiling point of 444 degrees centigrade. It is insoluble in water, and again, it is a poor electrical conductor. So covalent molecules, as you can see, are not very soluble in water. They are only slightly soluble or insoluble in water. And all of them are poor electrical conductors, and they have very low melting and boiling. Like the first two elements have melting and boiling points in negative, they're minus. But then we have some which are not minus as well, which are not negative. But overall, covalent molecules have low melting and boiling points compared to ionic substances. So these were all the properties of ionic and covalent substances. So these were all the physical properties of compounds, ionic and covalent. So this was it for today's chapter, bonding and structure. This is what we read in this chapter, and we've successfully completed all the learning objectives in this chapter. We've learned to describe and state, deduce, compare. Yep, we did compare, relate, and predict. By predicting, we mean that what are the physical properties of ionic compounds and the physical properties of covalent compounds. Now you can certainly predict. Now you know that ionic compounds have high melting and boiling points, and covalent compounds have low melting and boiling points. And usually these covalent compounds are insoluble or slightly soluble in water, and they are poor conductors of electricity. So yes, we can predict the physical properties of both ionic and covalent compounds, and we can compare both their structures and their properties, and we can describe their lattice, and we've learned to describe metals as well as lattices of positive ions in a sea of electrons. So this was a very fun chapter. As you can see, we've learned quite a lot in this chapter. We've learned how atoms actually bond to make molecules and compounds and ionic compounds. So we've covered a very interesting and a very important topic of chemistry. In the previous topic, we understood elements, compounds, and mixtures. That was the previous chapter, chapter 5. And so this was it for bonding and structure. I believe you've understood everything I've told in this chapter and will memorize it. Our next chapter is going to be chemical formulae and equations. So thanks for watching, and I'll see you in the next video.